podcast is brought to you by LMU Munich.
So first of all, let's thank the organizers for kind invitation, and also for the audience for coming to the talk early in the morning. And what let's see, so maybe I should write the title. So its title is Quivers, and the unbox the equations, and the three manifolds. And this is ongoing work, which is partly in discussion with Yuji Terashima, which will hopefully appear soon. So let's see, how does number work? 2, 3. And hearing other people's talk. Yeah, and I'm definitely tempted to write. There may be some other thing. So I'm just copying what he wrote here. Okay, and well, so this story is about about some curious connection between three-dimensional. Well, again, I'm going to have in the end, I'm going to have three n equal 2 gauge series, and it's related to the geometry of the three manifold, or more in physics language, it's going to be related to the physics of the Chern-Simons series with non-compact gauge group, like SL2. And of course, we already heard about this connection from Gray and Tudor, and I hope myself has been working on these topics for a while. But today, I'm going to talk about the connection, slightly different connection from what has been worked out so far. And the connection between what I'm going to talk about today and what has been discussed so far is a little bit unclear. Although I see many similar structures appearing, but there are some setups are different. So it's nice to know, understand the clear relations. But anyway, so let's see it's here. And so first, let me begin by giving the overview of what's let me explain all the ingredients which appear in my story, because there are a lot of things appearing, and it could be messy if I start talking about each particular one from the outset. And so in my story, I'm going to start with convex polytope. So this is a convex polygon, and in R2, or in more physics language, it's a toric diagram. You can place it on, you can add one extra direction, and it becomes the fan, or top dimensional cone of the fan. And well, for example, these are, I'm going to use this example where this is a convex polytope. So of course, the physics meaning is that there is an associated manifold, which are like X delta, which is the toric Calabi-Yau threefold. So this is the starting point, and the both sides of the story, the gauge theory side and the three manifold side, will somehow emerge from this data. And now, well, let's go to the gauge theory. And there are several ways to construct gauge theories starting from this data. And indeed, people have been interested in a lot of gauge theories are interested in toric Calabi-Yau threes, because whenever this is going to be the cone, and whenever there is a cone, you can probe the geometry by placing these three branes transposed to that. And then there is effective theory, which is a four-dimensional, in general, n equal 1. Maybe I should write n equal 1. Quiver gauge theory, which we believe flow to an interacting fixed point in the infrared. So, I mean, for example, a good example is that this is just a conifold, and this is the famous Krebanov-Witten theory. And so what I mean by Quiver gauge theory is that there's a graph, nodes, and arrows, and there are biofundamentals in between them, and like this. And we've seen similar quivers from Vasili's talk a few days ago, but this is a four-dimensional n equal 1 quiver, and also it's not conformal in UV, but it flows infrared to a certain non-trivial fixed point. So, I mean, the situation is slightly different from Vasili's talk, but we have similar structures here. And since it's for the n equal 1, it could be chiral gauge theory. So for example, there could be just one arrow going in this direction. So it's in general chiral theory. And well, and then what I'm going to do is that this is the four-dimensional gauge theory, and then there's one thing I can compute. So this is whenever you have a four-dimensional gauge theory with which flows in the infrared fixed point with n equal 1 or greater, and then I can compute some index. So this is a four-dimensional gauge theory. So whenever you have a four-dimensional gauge theory, you can place it on S3 times. So this is an index on S3 times S1. And you can show that it preserves certain supersymmetries. And in particular, well, for example, if you have S1, you can define a width index, but you could introduce some extra twist associated with some rotation symmetries, etc. And then, well, I will explain that later. But in general, this is not just going to be a number, but it depends on several chemical potentials. So there are chemical potentials that they are feature light P, Q, and U in my notation. But they parameterize, so each of them, roughly speaking, measures energy or the spin, rotation of the spin along S3, or the flavor charges. So there could be many flavor charges. So in general, this U is going to be a vector. So this is a certain well-defined series. So it starts from 1, which is a ground state, and it expands. And it's a power series. And there are certain numbers, which could be positive or negative, depending on whether its index is positive or negative. So it's a well-defined quantity. Now, whenever you have a four-dimensional gauge theory, S3 times S1, one natural thing is to just reduce the theory on S1, just shrink the S1. And then the resulting theory, so let's do that. I'm going to do two operations to this. But one operation is to do the dimensional reduction. Well, dimensional reduction is a little bit complicated in the sense that there is a twist associated with this one. So it's not really the usual KK reduction, but essentially it's just strict S1. And then, as you can easily imagine, since we are losing this information, we obtain something in 3 dimensions. And so we have 3-dimensional, and then the resulting theory has 3-dimensional n equal 2, well, supersymmetries. And we have 3-dimensional n equal 2 Quivers gauge series. And in this limit, we lose some parameters, but some combinations. Well, we are shrinking the circle, so all the chemical potentials goes to 1. But we can keep the ratio to be finite, and then we still have some parameters. And some of the parameters, so this is a partition function. And then, for example, there is a one-parameter deformation of S3, which preserving U1 times U isometry, which this is the one Craig was talking about at the beginning of the conference. And we have a partition function. And then some of the parameters become real mass parameters, etc.
What's B in the 40 language?
Yeah, so B is the ratio. So let's see. So since the circle is shrinking, all these P and Qs, all the chemical potential goes to 1. But you can keep the ratio fixed. For example, I can take the limit. P goes to exponential minus B, for example. Q goes to exponential minus B inverse. So B goes to 0, but small b, sorry, beta goes to 0, but B finite. And well, and then, well, sorry for writing in a small place, but also we can keep some parameters. So let's go mu, for example. So some of the parameters, so we just lose one parameter essentially, but the ratios we obtain. So this still depends on parameter B, as well as some parameters which are like mu. Yes, that's right. That's right. Yeah. So that's right. So this is a global symmetry charges. Well, chemical potential for global symmetries, and then after reduction, it becomes a real mass.
Excuse me. So if you have some two limits going to 0, right? The radius of S1 and beta.
Oh, well, beta is sorry, beta. Well, I think, but it's essentially the same limit. Yeah, because well, the chemical, for example, I mean, along the S1 there is a Hamiltonian, etc., and there is a factor of minus beta Hamiltonian. For example, as for the energy, there is a term like, sorry, if it's just a width index, there is a term like exponential minus beta times energy. Here we are doing more twists, so it could be minus beta times angular momentum, etc. But then that beta is really the cycle. Sorry, the radius, inverse radius. The radius of the S1. So that going to 0 is the same as this S1 shrinking. So that was the basic idea of how this reduction occurs. And maybe, I tend to forget to give appropriate credit to all these people. So, this has been discussed in a paper by Doran, Spiridonov, Bartanov, and also by Gatyan. There's a subsequent paper by Imamura who did this reduction. So, this is a superconfirm index, and defined in 2005. And this one is a relatively recent S3B by Hasama Hosomichi, and but since we now have two expressions, we can just take the expression, take the formal limit, and then just compare. So that has been done. But of course, this procedure is a little bit subtle because this S1 shrinks, and which means all the KK modes decouple. So there are divergences coming from the higher KK mode wrapping around this S1. So you have to regularize the divergences. But that's fine, and you can just neglect the divergences. And we see that these expressions coincide. So that discussion applies to any 4-dimensional n equal 1 gauge series and 3 n equal 2 series, but just apply that to this particular setup. And then let's see. Well, let's see. So this is the one side of the story. And as you can see from this blackboard, I want to write something on this side. And on the other side corresponds to the 3 manifold. So how does it arise? So, well, let's see. So this is becoming a little bit messy, but this is the setup. So this is the one side of the story. And there is the other side of the story. Well, to explain that, well, let's see. So I didn't really explain how this Quivers gauge series and toric diamonds are related. And that takes a little bit of time to explain, and I hope to do that afterwards. But the connection is that given the toric, there is a very systematic ways of starting from the toric diagram and going to the Quivers diagram. And that's sometimes called the fast forward, fast inverse algorithm, etc. But anyway, the name doesn't matter. And what you do is that, suppose that I'm given the toric diagram, and then I can construct the so-called zigzag path. Yeah, I will explain later what this means. But on a certain configuration of paths on the 2-dimensional torus. And from there, well, probably I should write it here. And from there, you can write down some graphs, bipartite graphs, or it's dual. Dual is the Quivers diagram. Well, if you don't know what the bipartite graph is, I can. So it's just a graph. It's just so for example, simplest example of the bipartite graph is that is this graph where the vertices are colored black or white, and the odd edges, any edge connect vertices with different colors. So for example, well, you could try to make more complicated example, but say the most typical example which appears in condensed matter system, etc., is this graph where white connected to black, black connected to white, etc. So this is a particular type of graph, combinatorial object, and well, sometimes these in this context of Quivers gauge series, these are called the brane tilings, and as has been worked out in a number of papers by Ami Hanani and his collaborators. Well, let's see. So the bottom line was that we have after some combinatorial procedure, we obtain some Quivers diagrams on the torus, and from there we could go to the Quivers gauge series side. Well, let's see. So I will hopefully explain that part. But to complete my story, I have to come to the 3 manifold, and the 3 manifold arises from something 2-dimensional, and something 2-dimensional is already here. So we have a bipartite graph or some zigzag path, etc., defined on 2-dimensional torus. So there is something 2-dimensional here. And the observation is that this quantity, which is defined in 4 dimensions, is actually the same as the partition function of certain 2-dimensional spin system on the 2-dimensional torus, which is defined from this bipartite graphs. From these graphs, you can define a certain 2D spin systems, And the statement is that first statement is that these two are the same. Well, I'm not using the Brockport too well, but hopefully the structure is clear.
The 4D index.
Yes, that's right, that's right. So the 4D index corresponds to 2D spin system. So somehow I see the decomposition of 6 into 4 plus 2 again. And then there is a counterpart of, well, I do the dimensional reduction, and also doing some, giving a, actually not just doing the reduction, but giving a web to some vector multiplet scalars. Well, I will explain later, hopefully. But anyway, after doing some operations, I still obtain a 3D n equal to the theory and some partition function. And then the second statement is that this is the same. Well, let's see. Well, this part is a little bit not very established, so I would like the dot. So this is probably related to the partition function, three-dimensional SL2 Chern-Simons theory on a certain 3 manifold.
What is this partition? Sorry, this index count geometrically?
Well, this index? Yeah, so it's index defined on the Hilbert space on S3. So if you like, you can go to the infrared fixed point. If you do
Usually geometric interpretation in terms of flattening out counting either curves or functions.
Oh, okay. So we want a more intrinsic Calabi-Yau 3 interpretation for this quantity. Yeah, that actually I don't know too much. I mean, to some extent, well, we have a geometric. I mean, for example, we are going to see some connection to 3 manifolds, etc. That says that a reduction of that could be understood from some information on toric Calabi-Yau 3, but it's not as direct as you might want. So probably you want some, say, define some moduli space from directly from the Calabi-Yau 3, and just the index of that, and that would be the same as for the superconfirm index. That would be a very nice statement to make, but I don't know that clear-cut statement so far.
Can you say how you get the gauge theory from Calabi-Yau?
Oh, okay. Well, let's see. Well, maybe. Well, let's see. So one way to say that is that. Well, one somewhat mathematical way to say that is the following. So given a toric Calabi-Yau 3, and then there are categories of derived categories of coherent sieves on this toric Calabi-Yau 3. On the other side, this is a gauge theory, but let's forget about gauge part, etc. And it's just a quiver. And from this quiver, you can consider define algebra, the path algebra, defined by just the concatenation of paths, etc. And then you can consider the category of the finite generated modules of that quiver. And the statement is that these two are the same, derived equivalent. That's the statement. In some cases, I worked that out, but and subsequently, a lot of mathematicians expanded that to many examples. But that's one way to formulate that. Or more physical way of saying that is that this 4-dimensional quiver gauge series, it has a moduli, classical moduli space of vacuum, which is a Higgs branch. And then that's identified with the toric Calabi-Yau 3 itself. So that's the statement. Because there's a cone, there's a cone, and the 3 brane probes that, and then the 3 brane probes the whole geometry. And these 3 branes. Sorry?
That's one of the branches.
Sorry?
That's only one of the branches.
Yeah, one of the branches. That's right. There are other branches too. Yeah. Yeah, that's right. Yeah, that's so maybe to make statements correct mathematically. So probably it's a certain connected components of the moduli space. Defined by GRT quotient, etc. But anyway.
Sorry, when you mentioned 3D Quiver theory on the bottom left-hand side, do you mean Chern-Simons type as well?
Well, let's see. Actually, let's see. So, well, first of all, if you just do the dimensional reduction, and then there are no Chern-Simons terms, we just do the dimensional reduction. But I'm going to do some further reduction preceded to that description. And then that gives a web to some certain field, and then just send to infinity, etc. And then you, due to the parity anomaly, etc., there is effective Chern-Simons term appearing after that.
So at one loop, you can generate.
Yeah, that's right.
Does this mean that in the 4D case, you have to have a chiral type quiver, right?
Mm-hmm.
Chern-Simons.
Yeah, although the story itself does work for any quiver so far. Although there could be some subtleties. For example, I could take to be n equal 4 theory, and then 3D theory has n equal 8, and there are certain arguments why the naive computation of n equal 8 doesn't work, etc. So there is a good, ugly, bad classification, etc. So, but generically, I think this scheme works. So, and well, let's see. So this is defined on certain 3 manifold, maybe here, and as I said, this is a little bit speculative part. And one simple thing when we do discuss Chern-Simons series, so let's see, there is a parameter b, which is here, and it's a certain deformation parameter of the 3 sphere. And then there is a corresponding parameter t or k, depending on the preference. So this is a level of the Chern-Simons series. And the indication is that b squared is equal to k, 1 over t. There could be some one loop corrections. So this b and t are related. So I roughly write b squared is 1 over t. They are one loop corrections. But
so are you thinking of both sides here as just formal perturbative expansion?
yes, that's right. Well, of course, you could try to make even stronger statements, like they regard this as SL2C and state sum over solid points, etc. But I haven't gone that far
really
here.
You just mean, so that's why you don't have to say whether you mean SL2C or SL2.
Right. So in my context, it's the same. So it's just a holomorphic part of the partition function. So they are the same. That's right. So for my purpose, it's really the same as SL2 or C, or holomorphic part of SL2C. But this, I'm not sure if this is really true. But one thing I can do is that simplify the stuff. And then one way to simplify the computation in Chern-Simons theory is just go to the classical limit. And of course, if you go to the classical limit, we don't have to do any loop computations, etc. And the things simplify considerably. And on this side, let's go to the limit t goes to infinity. So in Chern-Simons, let's say t goes to infinity. Let's go to t goes to infinity. That's the classical limit, because Chern-Simons theory coupling is 1 over t. And then the leading contribution scales like a volume of the m. But there is a Chern-Simons term, but actually I haven't. I'm less confident about that part. But at least volume is the leading part of this M3. And then there is a corresponding statement. So if you go send t to infinity, and that's the limit where b goes to 0. And so I have to take the limit b goes to 0 to this expression. And the interesting part about this squashing deformation is that if you have S3 and send b to 0, and that effectively reduces to S3b reduces to R2. Well, of course, if it's b is finite, this is still finite, but it diverges. And times S1b, where b is very small. So effectively, we are doing dimensional reduction again. And then here we have the 2D2, theory. And in the 2D2, theory, there is a notion of effective twisted superpotential. Well, let's go 2D. Again, Quivers gauge theory. And this is a twisted superpotential. Okay, maybe I'm going too slow, but anyway. There's effective superpotential, twisted superpotential. And the statement that these two are the same. Or I can make a more precise statement, which is that this depends on, this is a function with respect to the scalars, vector multiplied scalars, or the scalar component of twisted superfield, defined from the derivative of the vector multiplied scalar. So it's complex. So it's the scalar coming from the dimensional reduction. So for the gauge field has 4 components, but if you do the dimensional reduction, there are 2 modes which become the scalars, and then these are complex scalars. So this is a quantity, and this is a function which depends on that. And then there are corresponding parameters. This is a 3 manifold, and well, we heard about 3 manifolds, etc. Yesterday as well. And if you have a 3 manifold, say for example, let's write tetrahedron. And then there are modulus of this tetrahedron, like dihedral angles. So you can deform, push it forward this way, and then deform it, etc. So there is a modulus of this tetrahedron, the dihedral angles. And so there are some modulus, how to change the geometry of the 3 manifold. And then there is a corresponding parameter. And then there could be some constant part independent of sigma. I'm slightly annoyed by this part, but and I haven't worked out whether this is 0 or not. But anyway, this is the statement. And in particular, you can take the derivative of this and obtain a classical vacuum. the derivative of this saddle point equation for this is the classical equation for the classical vacuum, and that's translated into the Green condition for the hyperbolic three manifold. Sorry? Yeah, okay. So I'm going to come to that. So, and the way to M3. So how do you obtain M3? Because so far I just said M3, but I haven't seen. So, and this M3 is defined like as follows. So I really haven't explained how this bipartite graph arises. But let's just suppose that there is a huge torus, and then there are some bipartite graphs on it. Let's say, for example, let's take this one, for example. There's a bipartite graph there. And this is obtained from this toric curve, you see. Now, what they're going to do is that for each phase, well, first of all, for each phase, there is an associated ideal polyhedron. So what that means is the torus. So this is a two-dimensional torus, but you can, well, embed it into the universal cover of that. So each phase could be regarded as a phase inside R2. And then this R2 also lies on the boundary of the hyperbolic three manifold. Well, there is an infinity as well, but so this R2 could be regarded as the boundary of the hyperbolic three manifold. And so the hyperbolic three manifold, if you're not familiar, is that the H3 is simply the manifold defined by dx1, dx2 plus dy squared, y squared, where this y is this direction, and x, y, x2s are these directions. Well, maybe some string theorists might know ADS3, which is a weak rotation of this one. But anyway, and this is the y direction. So whenever there is a polygon, here I could write a polygon at the boundary of the hyperbolic space. And then what I'm going to do is that I lift that to 3 dimensions. I'm going to draw lines here and there. Oh. And I'm going to draw, let's see, the geodesics along that. So, and there and there. So geodesics in R3s are the circles, for example, the circles whose centers are at the boundary. And then there's lines like this. And then also there are faces. You could try to fill that in the middle. And then the simplest example for this is that, for example, suppose that, well, in this setup you don't obtain the triangle, but suppose that you have the triangle, and you could try to do the same thing, and then there is a region which is above this line, and that's known as the ideal tetrahedron. And this is just a generalization of that to n polygons, so that's why I called it ideal polyhedron. And certainly, you could, if you like, you could try to divide into ideal tetrahedron by trivially dividing this boundary polygon into triangles. And you're going to do the same for each of these faces. So for each face, say this face F, there is going to be associated ideal tetrahedron delta F, and then you could construct a polygon as a union of all these over faces. And then this is almost this three manifold, except that this three manifold is defined by gluing the identical copy of P from the one is on one side of the one P is on one side, but they just prepare the same thing in glue. So you basically take the same thing from the other side, and it just glue by making identification at the boundary. So it has a boundary, but it's a nice boundary, geodesic boundary of the three manifold that you can just glue. And somehow some mathematicians have studied this type of decompositions, and this three manifold is going to be some link complement. And link complement. So this is going to be some link complement. Not in S3, but in torus times the interval or something. A little bit funny space. But it's in any case, it's defined as a link complement in certain three manifold. So
Sorry, so I didn't quite understand. So P here is the union of the faces, and the faces are in H3, or what?
no, let's see. So P here is the union of the tetrahedron, ideal polyhedron, which is above these faces.
But why is that not all of H? The way you try to.
Oh, okay. So maybe I can explain it in one more different way. Let's see. Yeah, I mean, for example, for tetrahedron case, well, I really probably should. I mean, there are some surfaces which are, again, the geodesics of H3. And that's why this is not the whole region above S3, above this triangle. But I can explain a slightly different way as well, which might be clearer. So to explain the same thing in a different setup, well, it's the same if you know the hypergeometry, but it might look slightly different. So again, I have this graph. And, oh, I remember I have these wonderful color chokes, so I should use it. And suppose that I have a graph like this. And then you can try to draw a set of circles. Let's see which color is good. Probably yellow. You can draw a circle here and there, and here as well. Well, it's become messy, but there is another one here as well. But you can try to draw a circle. So the circle, so we draw a sequence of circles, set of circles, such that all the vertices pass through the circle. And of course, it puts some constraints on the length of the edges, etc. That's some extra information. I mean, all these people studying Quiver gauge series, etc. This was abstract graph, so there was almost no meaning to the length. But there are some discussions about, say, the length. I mean, changes the gauge coupling constant, because roughly it's realized by D brane. So these are the faces represent some D brane region. So its area is a coupling constant, etc. Well, probably I'm not sure if I have time to explain that, but there are some interpretations like that. But here in this context, this is not a topological graph, and there are some information as to the length of this graph. And that length is actually the same as the deformation of this hyperbolic three manifold, which I wrote somewhat telegraphically as sigma. And that's the deformation parameter. In any case, so I'm going to draw a set of circles like this. And
are you just putting a hyperbolic metric on T2 times an interval or something?
yeah, T2 times the half line. Yeah, half line. Yeah, that's right. I mean, for each of these, if you just concentrate on this one of these polygons, it just doesn't make difference whether it's a torus or it's torus or R2.
And that's what M3 was also? What was the gluing that you said?
Yeah, the gluing is you just take two polyhedron from one side. So it's defined, there are some regions there, and it's the region above, and there is another, you take another thing and just glue them together by making identification at the boundary.
So from the point of view of M3, I mean, what's the significance of this was a bipartite graph, right?
Yes.
So how does that play into anything on the other side? I mean, the polyhedra you construct don't seem to care what the color of the vertices are.
Mm-hmm. Yeah, that's true.
So does that appear anywhere on the other side?
Well, on the other side, mening this side.
Yeah,
the
three manifold. Yeah.
Well, I think it's for example, on the three manifold side, it's not too clear. Although there's one somewhat mathematical, I'm not really answering the question, but there's one mathematical fact which which is related to that. And some mathematicians are interested in this configuration of circles on the plane, and they call it circle patterns. But whatever the name it means, they were interested in doing some discrete version of conformal transformations. So so roughly speaking, they try to put the constraint that angles are preserved under certain deformations. And roughly speaking, the change of these sides of the circles, etc., represents the geometrical version, so discrete version of the conformal transformation. And then what they found is that if you try to impose the condition for all the vertices, that's too strong, and then they are not interested in discrete conformal transformations. So I forgot the precise condition, but for discrete conformal transformations defined by having certain property only at these Bragg vertices. And that one seems to be the good definition somehow. Yeah, if you really ask me why that's the case, I really don't know, but that seems to be the case. So there are at least some mathematical definition, motivation for doing that. And of course, if you go to this Quiver gauge theory side, there are a lot of motivations. But let's see.
You have the three words
Sorry.
about the interpretation of M3. So, I mean, you can say that you get these quiver gauge series from brains at that singularity of the historical Lambiao, and then can you give some interpretation
Oh.
to this M3?
Yeah, let's see. Well, not really, but I have some hint. But let's see. Before answering questions, since I started writing this, so let's see. Let me first finish how this is useful for understanding M3, and then come back to your question. Okay. So first of all, I was drawing these circles, and whenever there is a circle, and then you could draw a hemisphere. Oh, well, this doesn't look like a hemisphere, but hemisphere whose center is at the boundary, at the center of the circle at the boundary. And then it's known that this is really a geodesic surface in H3. And what we have is, in general, there are several circles. And then there are several circles like this, and we just put in this hemisphere again, a lot of hemispheres one by one. And of course, there are intersections between hemispheres. But the end product is polygon. Polygon is defined as the complement of all these hemispheres. That's equivalent way of saying this. That's equivalent to what I said previously. But this is the definition of the three manifold.
Do you have a simple example of three manifold giving some simple brain planning, for example?
Well, yeah, I mean, to some extent, for example, but there are some questions about whether we can this partition function applies. But let's just naively take n equal 4 theory. And as you know, the bipartite graph is a hexagonal lattice. And in that case, well, I have just one ideal hexagon. And it just grew them together, two together. So that's the simplest example of the three manifold I have.
So the partition functions you're going to construct, are they related to what Bajanov and company?
Yeah, exactly. Yeah, so I'm really, probably I should emphasize that I really heavily using the hint side, their result very heavily to some extent. So for example, I said that this is a 2D spin system, but that's almost the solution to this YBE constructed by Bazanov and Sergeyev and Mangaev. And yeah, so they first found the version for this one. There was first of all, historically, there was solution to the YBE constructed by Hadeev and Volkov, and there was a generalization of that by Sergeyev. And yeah, that's right. And then they went on to the elliptic side, and quite recently they have SUN generalization of that. And if you look at the formula, SUN generalization is, of course, the same as SUN generalization index, except that there are some minor differences because I really insist on the bipartite property of the graph, and there are some physics reasons why I insist on that. And in order to preserve that, I have to do Yang-Baxter move always twice, roughly speaking, in order to preserve bipartite property. Whereas these people are, Sergeyev and his Babanov, these people are interested in their statistical mechanics. So they really wanted to construct something invariant under single Yang-Baxter move. So that was the difference. And consequently, there are some differences in normalizations, etc., which I really don't need for that purpose. And to some extent, they have the SUN generalization of this spin system, but they couldn't show analytically the invariance of the partition function under single Yang-Baxter move, etc. So there is still higher component case. Yes. Yes, that's right. For higher Planck case, they didn't, but they do the perturbative series expansion and try to check that, etc. Yes. Yes, that's right. And indeed, they also discuss the connection to discrete conformal geometry. And then some mathematicians like Springhorn, Bobenko, etc., have been working on that. So I'm just really using, all these developments. But anyway, since there was a question, maybe I should come to the brain comment on the brain realizations. Okay. Well, as I said, probably I want to keep this part. As I said, it really doesn't answer the question of how this M3 arises from brain construction, but it almost gives a good clue. And well, so let's start with the D3 original picture, the toric-Carbiel 3-fold case, the toric-Carbiel 3 over there. And we are probing that geometry by D3 brains. And so the setup is D3, so I don't probably even have to write it, but D3 013, and Carbiel is in all other directions. So this is the setup. And well, of course, one complication is that this Carbiel 3 is complicated, so sometimes it's useful to take the TDO. And then we are not really getting rid of the curve things, but this is slightly useful. So let's say 4, 5, 6, 7, 8, 9, and let's say that 5, 7, 9 directions are the circled directions. So they are R2 times R2 times R2, or most specifically speaking, this Carbiel is toric-Carbiel 3, so they are U1 rotations. So, and then let's regard these 5 and 7 directions as the U1 rotation along the toric-Carbiel 3. But roughly speaking, this is just the rotation of 4 and 5. And then this is just the T duality along 5, 7. And then we have the configuration like 5, 5, 7. And we have NS5 brain. And of course, since this Carbiel 3 is complicated, this NS5 brain is complicated. But it's not too terribly complicated in the sense that it laps a certain curve, sigma, in this 4, 5, 6, 7 brain. And the sigma, so if you define coordinates, x4 plus ix5, and y equals x6 plus ix7, and this is just a polynomial, Roland polynomial with respect to sigma is a Riemann surface such that some polynomial, Roland polynomial, with respect to x and y's equal to 0. And if you like, you can try to take T duality once more, and this is D5 becomes D6, and the Carbiel 3 becomes the mirror of the Carbiel 3-fold. And so this is for people working on mirror symmetry, etc., this is really the curve which appears in whole equivalent buffer mirror of the toric-Carbiel 3-fold. But in any case, this is in this construct, it's just a curve of the D5 curve locked by NS5 brains. And yeah, so I worked this construction with my colleagues in Tokyo some time ago. It's actually 2007. In any case, and let's see. So, and then let's see. Well, this was the brain configuration for the n equal 1 theory. But let's see. And then this is to some extent useful for understanding how this crazy bipartite graphs arise. And the statement is the follows. Let's see where I should use. Maybe I can try to switch to. So this sigma is a surface in four directions, 4, 5, 6, 7 directions. And well, of course, it's complicated. It's hard to visualize. And so it's one way is to always good way to visualize is to project into lower dimensions. And there are some nice good projections. Say, suppose that there is a sigma. This is a p, pxy equals to 0. But let's project that onto 5, 7 directions, which are this just the torus directions. So the end product, the image of this curve is inside torus, two-dimensional torus, by definition, because it's 5, 6, 7 are compact. And then I have a certain graph in certain image in the T2. And then the statement is that actually this graph, that projection almost knows about this bipartite graph. What I mean is the following. So let's take, say, simplest example. Say in some cases, say conifold, we have a graph like this, and in this toric Carbiel, sorry, in this T2. And in this example, if you try to plot this image, but image is not the core neighbor somehow. Well, because it's the dual objects projection into 4, 6 dimensions directions are known as amoeba. But in any case, whatever the name, there are some projections, and the regions after the projections are roughly like this. Oh, this I'm not doing writing very well. Well, I'm too rough. And if you do the projection, well, this is a surface, and the surface projected to 2 dimensions. So there is something 2-dimensional appearing. And it happens that the image of the map are these regions. So the result is that, so one way to say that is that the image of the NS5 brane. So in this brane configuration, we have a torus because D5 brane laps a torus. So this torus is a D5 brane, if you like. And the image of the NS5 brane gives a shaded region. Shaded region which appears here. And well, if you actually plot this image, there are some smoothings occurring in general. But roughly you can see the structure, and you can try to extract these asymptotic lines from certain arguments. And also, well, there are differences of black nodes and white nodes, and black and white that corresponds to orientation of NS5. So what that means is that we have D5 here, which is a torus, and some complicated NS5 brane, which wraps a Riemann surface that I consider projection. And sometimes, in some parts, say, well, I was writing in yellow, but no, here, not this, here, not here. Sometimes, let's see, I was using yellow, so in some regions, the orientation of the NS5 brane coming from the reduction is the same as the orientation of the D5 brane. Or sometimes the orientation is reversed. So roughly speaking, whenever you have a graph like this, there is a twist of the shape of the NS5 branes, and you see the different shapes. And so first of all, that's the geometrical interpretation. And I can try to go on to use this picture to show why the Quiver gauge why this gives a Quiver gauge theory of the salt, etc. So that probably I won't go to that part because I want to come back to the question of how to relate that to Riemann manifold. But what I want to say is that first of all, these combinatorial constructions have a brane realization. And now that's for 4-dimensional n-equal gauge series. As you can see, this is a 4-dimensional n-equal 1 gauge series. So these are for the n-equal 1 SCFTs. Now I have to do the same reduction procedure too. So I did the dimensional reduction and the giving a web, etc. I have to do the same thing to this brane configuration. And so in order to go to 3 dimensions, I take a T-duality along these 3 directions, compactify 3 directions, and take T-duality along 3 directions. And we have a configuration 0, 1, 2. And then S5 brane stays the same. And 5, 7. And if you like, you can lift it to M series. Well, I think you can raise it by adding 11 directions, and you have N5 brane, and then 5 brane, 0, 1, 2, and 3 is not here, 5, 7, and there's 11 directions. And there's Riemann surface, and then there's, 3. And, well, I forgot to say that in general, if you want SUN Quiver gauge series, we want these 3 branes, and these 3 branes for it will be just a 1 Calabi 3. So apparently we have N and 5 branes here. And since these are all these, so there was original 5, 6, 4, 7, and then say 8, 9, 11 directions. And all these are compact directions. So this M5 brane laps the T3. These parts, 5, 7, 11 parts of T3. Whereas this M5 brane laps, so this M5 brane laps the 3 times the Riemann surface. And this is a Lagrangian in this whole space. This is a Lagrangian inside 3, 4, 5, 6, 8, 11. Which is R3 times T3. So this is going to be a Lagrangian. And this Lagrangian intersects, so this Lagrangian intersects this torus by one cycle, because originally, I think this here is this. This surface intersects with 5, 7 with one cycle. So it intersects with one cycle. So it's such a composite system in M5 branes. And so I strongly suspect that, well, probably I should write R3 or something. And well, maybe I should write R3 anyway. So I think this is almost the 3 manifold I'm talking about, probably. But except that it looks slightly different in practice. But so this is a very long answer to your short question. So I think there should be, from using these duality chains, there should be a lot of direct connection of this 3 manifold to the 3 manifold I was talking about. And indeed, structure is to some extent similar in the sense that here the thing I was explaining is that, which I deleted already, but is that whenever you have the 3 manifold, and then you can project it to two dimensions, and that almost gives this bipartite graph, which is nothing but the shape of the brane. So roughly speaking, but very colloquially speaking, this sigma is nothing but a projection of M. So that was the structure which I found here. And then, well, this is almost very similar to that. So roughly speaking, well, this is not really roughly speaking. This is very similar to M. And again, I have some extra dimensions emerging, which is the compact directions. And so I think that the rough structure match, but of course there are some other things. But you have to work out the detail really. But I should emphasize that, for example, the equality I was talking about here. Sorry.
So the roughly in quotes is saying that M is something like a circle vibration over sigma. Is that?
Yeah, that's right. Yeah, that's right. That's right. Yeah, roughly. Yeah, I think so. Although one thing is that there is a one reduction procedure which I performed here, and I have to do the reduction procedure here as well, brane configuration, and I haven't done that. So that probably gives some further deformations to the geometry, presumably, and that probably explains the missing link. But I think it's true. That's the rough structure. And curiously, this brane configuration, some people, well, for example, there's a paper by Sang-Min Lee where he was interested in M2 branes 3D series, which are due to M5, sorry, 3D series, Quivers series. But in that case, he has a chance thermostat, but he was trying to write down the counter. So he was studying ADS4 CFT3, and he wanted to do a counterpart of this brane configuration for this configuration for ADS5 CFT4, and this was a natural generalization indeed. So I somehow obtained the same brane configuration, but again, the setup seems to be slightly different. So there are a lot of confusions here, but at least so this is the structure. Okay, so I think I still have the 5 minutes. So and then let me. Since I have 5 minutes, probably I don't have time to go into detail of this construction, but rather mention one connection to the topological string theory, which comes in, and the physics of the BPS state counting. And then the story goes like follows. So this is already a messy figure, but I'm going to add some more extra ingredients. Maybe I should use a different color. Let's see which color I want. I hope this one works well. Oh, probably this one. Let's use the color so people are not confused. Well, suppose that I have a toric curvature 3. So I go back to toric curvature 3 again. And then you can do the BPS state counting. What I have is that I have typical D2, D0, D2, D6 systems. You can try to add D4 as well, if you like. So these are toric Caviar series, and there are various compact 2 cycles, 4 cycles in the story. And these D2, D4, these effectively could lock 2 cycles, 4 cycles in the toric Caviar. And they look like particles in 4 dimensions. And so without these D-branes, since it's Caviar 3, 4-dimensional part has 4-dimensional n equal 2 significance. And these D-branes look like particles inside it. And so there's an issue of how to count the number of degeneracies, etc. And there are wall-crossing phenomena. And but that's a general story. But there are some particular particular nice story about this toric Caviar 3, which is that we can count the BPS degeneracies exactly. And that's again done by this diamond model, etc. And what we did there is that I defined some BPS partition function, and it's defined as a charge of the D5 branes, charge of the D2, D0, D4, and some degeneracies, and there are some chemical potentials. Well, let's say Q, gamma, etc. Roughly speaking, and these are the BPS degeneracies, the number, or if you like, generalized DT invariants or generalizations. Although I'm not going to really discuss wall-crossing phenomena, but there's a partition function you can define physically for the gauge series. And then this is identified as a certain dimer partition function, which is defined on R2, or we call it crystal melting in honor of the Okun-Koreshi buffer, which is, so what we did is just generalize their construction to more general toric Caviar 3s, but we have a dimer partition function. And this is the same, well, up to some signs, etc., is the same as the BPS partition function we have shown. So again, we have dimers appearing, and we have the partition function. And some time ago, we discussed some dynamic limit of this partition function, or some dynamic limit meaning there are some chemical potentials here. The chemical potentials are typically like exponential GS, where GS is a topological string coupling constant. And in that context, we took the limit where GS goes to 0. So that's the limit where this all the chemical potential here goes to 1. And that's the limit where this crystal smooths to a smooth geometry. And well, in that limit, and then of course, if you do the compute the partition function, it diverges, but we can regularize it. So let's take this limit, and GS goes to 0. And in this limit, the partition function diverges because all the chemical potential goes to 1. But instead of doing on R2, we could first start on diamond model T2, regularize it, and then send that to infinity. So that's very usual way of taking some dynamic limit in statistical mechanics. And after some computations, and after a little bit of assumptions about what kind of toric Caviar 3 I consider, and then I have the normalized partition function. So let's consider limit n goes to infinity, 1 over n squared, and Zn, where n is this is the partition function on the torus with size n times n. So it's really the times some dynamic limit. And this takes a curious form, leading in some variables. Well, I really should stop, but a sum over the edges of this bipartite graph. And there are some parameters, CE, and log 2 sine CE, and 2. And there is a function called the Lobachevsky function, which appears in the formula of this partition function. There is a factor 1 over pi or something. But in any case, and this E runs over the edges, and this C to E are some parameters associated with the edges, which come from the weights of this diamond model. So I choose a particular parameterization of weights of diamond model, etc. So there are some details. But in the end, so what I said is that let's start with the BPS partition function, which in some chamber is the same as a topological string partition function. And just took the genus 0 limit, so it's going to be the prepotential F0. And that's going to be given by this expression. And interestingly, the reason I'm talking about this is that this part, the sum of this Lobachevsky function, is exactly the same as the volume, which I was talking about here. So this is the equality. And then this works as a certain Legendre transformation of the partition function. So I mean, I know there are a lot of interesting connections, but but here in this story, but there are some subtleties in D4 branes, so I would rather not include D4 branes here for safety. I mean, yeah, so crystal melting itself, I mean, up to this point we have the partition function, but there are some limits, some subtleties about how to take the limit in the case with D4 branes. So I should say the U1 case in the 40K series. So, and this limit has been discussed. Sorry, yeah.
So everything in orange was subject to wall crossing behavior, but everything in white was not.
Yeah. So actually, but here, so actually, I'm doing this in the so-called non-committed DT chamber, which is just a particular chamber here in this story, and so I'm freezing the wall crossing degrees of fear here. But of course, there is a question of what is there any counterpart of that here there. But one subtlety is that well, the wall crossing phenomenon. At least you have to take a scaling limit in the following sense. So say if you cross the wall just one wall, for example, in this crystal melting, the shape of the crystal is almost the same, except that you add one atom on the top.
I'm wondering if there's something happening in this GS goes to 0 limit that's somehow saying.
Yeah, so I think what you can try to do is take the limit where GS goes to 0, simultaneously crossing some number n of the walls, keeping this GS times n fixed, for example. And I think that in that limit, I think you should reduce the Kähler modulus of the Calabi 3, etc. So you can definitely try to add some extra information there. But at least in some chamber, we obtained this expression. And it seems to fit nicely with this again. So I already said that the story is about two connections, but there is one more connection which appears here. And there is a question of how to understand it really more physically, how this connection arises. And I think it's interesting to explore this further. Let me stop here.
Thank you very much. Other further questions or comments?
You see potential higher upstairs that we say.
Oh yeah, that's
And the other partition factor.
yeah, yeah. I mean, the superconfirm index could have some counterpart. Yeah, I think if you look at the figure, that's an obvious question. But somehow, well, for example, if you go down here, the YBE, etc., is essentially the pentagon of the quantum Taylor version. So essentially, well, roughly speaking, one of the concrete questions you can ask is whether there is an analog of the pentagon for elliptic gamma functions, roughly speaking. And I know some people actually have asked the question already, and some experts like Speedy Donovan, but there are no such things so far. But I think it's looking at these figures, it's conceivable that we could maybe extract some instead of doing the partition function, we could, as again Martin was saying, we could try to define some action on the flat connection on the 3 manifold and try to extract some indexes. I think it's very conceivable. But I just don't know how to do it concretely now.
Well, it's Yang-Beck's equation in the title. So this is presumably just the equation which assures in terms of the building of the, say, triangulation environment system.
Mm-hmm. Yes. Yeah, so I think actually what happens is a little bit subtle in the sense that sometimes if you do this, well, if you go down to 3 dimensions, there are.
It probably then appears in the guise of the star triangle relation.
Yeah, that's right. Indeed. That's right. So sometimes after the operation, you have extra circle appearing, but that extra contribution cancelled by some constant part which I wrote here, constant part. so that's the structure. Yes. That's already explained in the paper Bovenko and Springbom.